Previously we were looking at data that came from aluminum test coupons that had been subjected to repeated alternating stresses, and we talked about the stem and leaf plot that gave us a numerical picture of the data. Now we're going to talk about a pure graphical technique called the histogram. It's going to be very similar to the stem and leaf plot. In fact, we're just going to rotate the stem and leaf plot 90 degrees. And note that overall shape that we get. We talked about this a little bit before. And in this particular case, we've discretized the data in terms of 100 units. Right, going from here, 10 to 11 was actually 1,000 to 1,100. In a graphical sense, all we've done is the exact same kind of thing. We have this, what we call the bin width is units of 100, and we've just plotted then how many of the data points fit into that particular bin. So this one would have 6 in the 1,000 to 1,100 bin. Now, this particular chart was produced out of Excel, and I had to go to some lengths to get this to even come close to the way it should look, and that is that these bins should butt up against each other, and they should be adjacent. The default in Excel is to have gaps in between, so that actually gives you a suggestion about how you can change all that. Is if you right click on the data series and format the data series, you can then go in and change the gap to 0, and that will close that up into a more appropriate thing. The other kind of irritating part about the way Excel does things for this particular kind of data is that it doesn't really put the labels in the right place. And that's because this isn't really intended for an analysis tool of numerical data. It was really more of business data, and that's a different kind of world than where we are in the science, math, and engineering technology world. So these labels are really a little goofy here, but they're printed there in the center of the bin. They really should be printed where the axis tick mark is at. There's a way to change that, but you have to go through a lot of steps to make that happen. All right, and if you happen to know a shortcut to do that, let me know. I'd be pleased to find out. All right, so big picture here, though, is that we do have an appropriate kind of diagram, histogram. If you use something like Minitab or SPS or MATLAB, they will create histograms in a more typical, conventional science, math, engineering, technology kind of sense, where you don't have to do quite as much manipulation and effort to get things here. We have, again, the number of cycles to failure on the x-axis, and the frequency is the vertical axis, hence why this is called a frequency histogram. And we talked in Module 2, as we introduced the ideas of how to visualize the probability mass models, and then in Module 3, as we got to continuous random variables, the notion of the discretization issue of, well, what should the bin width be? What is the right kind of thing? If we go to more bins, that increases the resolution, but you'll note down here that our data becomes choppier. Data in the sense of the picture that we have is choppier. We have a lot more bins that only have 1 in them. Right? You see here where I've rotated the labels a little bit to make them look like they're headed towards the right-hand side of the bin. I'm sorry, the right-hand side of the tick mark. And we could go even smaller and smaller in our resolution, but just like in an actual photograph or that is a digital photograph or DVD, a movie, if you get in too close, you lose the bigger picture. You get almost too little information on the big scale. So we might go, say, the other way and use larger bins. And so now we have bin widths that are on the order of 200. And typically you're going to want to use bin widths that are constant. Occasionally you might do something a little bit different than that, but it's far more common to use common bin widths. If you don't, that's where you get into this notion that there's lies, damned lies, and then there's statistics, and that you can always lie by using statistics. Well, you're not really lying, it's how you use them. And if you start changing bin widths around but you don't plot the bin differently, then that's one of the ways you can tend to maybe unintentionally or intentionally misrepresent the information. Right, now note here we have 1, 2, 3, 4, 5, 6, 7, 8 bins that we're using. Really 9 and 10 if you consider that we just have one data point out here. It was the outlier that was sitting out there. And we still retain the overall sort of shape that we see in this case. We could go even broader in our bin width to 400, and we still, in this particular case, kind of have retained the overall shape of the distribution. But note that we really have changed what we see happening down here at the bottom end, where we had that one outlier down here at 375, and then we had to go all the way up to beyond 700 before we got to the next one. Big, large gap. The significance of that gap in this data is lost as we go into this larger bin width. So it does kind of raise the question of, well, is there any law or rule that you're supposed to use for creating these? And the overall rule of thumb that many people use, that by the way is abbreviated ROT, is to use square root of the number of observations as the number of bins. Right? And so square root of 70 in this case is about 8.6. And rather than going up to 9, what I did was said, okay, I'll get rid of this one, I'll use 8, and 8 just worked out very convenient as I went from 2300 as a max here, 700 there. I made a nice number of 200 as my bin width. That's important to make a nice number, because you're going to have to come back and interpret this, be able to read it, and so using some arbitrary judgment here to come up with what you ultimately use is a good thing. So that's why it's a rule of thumb, not some hard and fast thing that thou shalt must do. And it all depends too on what your software package will allow you to do easily. Okay, so these are the frequency histograms. They're useful, but I say it like that because they're only sort of useful. What would be a lot more useful to me is to know not the frequency of in the histogram, but typically I want to know, well, how often is my data within a particular region. In other words, what I want is a relative frequency histogram. Such as what we have here. So here's the same one where we've got the bin width of 200, but notice that the relative frequency has changed. And all we've done there, of course, is to take the frequency and divide by the number of observations, that is the total number of observations. So in this case that would be equal to our frequency divided by our n, which was 70. And now if you decide to kick out one of the outliers, this one that was down here, the 375, well then of course this would change to be this would change to be 69. On the other hand, other people, what they'll do is they'll use not n, but they'll actually use n plus 1. They do that because they recognize that this is a subset of the overall population, in this case the population of fatigue testing on these aluminum test coupons, that they haven't exhaustively done all possible aluminum coupons that could be produced ever. Right? You're always doing some sort of smaller subset. So they're recognizing that by adding this plus 1, so that when they come along and do the cumulative frequency histogram, that as they plot this up from a real small number and go up the step ladder, right, always increasing, when they get up to this value, this turns out to be, it turns out that the way I calculated it, it was at 0.99, right, rather than 1.0. And of course, that's the cap. And if you're going to really do this properly, well, you wouldn't have that, right? So that's a little sloppy. It's not a really great cumulative frequency histogram. And that's also an indication that, well, gee, someone, myself in this case, didn't take the extra time to really nail this down. It's one of the things I don't like about using certain packages that aren't really intended for doing statistical analysis, or creating these particular kinds of charts, because then you have to go through that extra kind of step, and it doesn't look quite as professional as what maybe you'd like it to be. Suggest to someone that, does that person understand that you can't have 120% cumulative frequency? I mean, okay, I'll accept in sports that someone can give 120% effort, because it all depends upon what it's relative to. But when you're talking about percent of the data, it can't be more than 100%. And that's why people do the n+1, because they don't want this number in this observed data to be exactly 1, because, gee, when you go do the next one, you might have more out here, right? And when you compare between the two, that might look a little funny. And so they do this artificial thing of kicking it up by 1 as a stylistic kind of measurement. And that's all it really is a stylistic approach to doing this. Right, so those are the 3 different typical histograms. The frequency one you see quite often, especially when people report out the results of exam scores. But the relative frequency histogram is probably used even more commonly, and depending on what it is you want to do with the information, the cumulative frequency histogram is perhaps even used more so than all of the rest of them.